Hello and welcome. I hope you are doing well. My name is Mustafa, and today we will be doing a quick concept review for Exam 6. In this video, we will be covering the trapezoidal method, Simpson's 1/3 rule, and Simpson's 3/8 rule. The goal of this concept review is to help you recall some background knowledge required to successfully code these methods on MATLAB, and hopefully that will be of help for you on your test and in future uh, applications for numerical integration methods. Now, the first topic we will cover is the trapezoidal method. The trapezoidal method is a first-order polynomial approximation. Now, what does that mean? This means that the unknown curve is approximated linearly, as we can see right here with the red line. Now, this method uses 2 points and one subinterval. As we can see right here, here's a subinterval, and here are the 2 points that we're analyzing. And this method is more accurate compared to zeroth order methods that heavily overestimate or underestimate the curve. Now, what do I mean by that? I mean, if you were to draw a rectangle like that and then try to find the area for that, you would be heavily overestimating, versus if you were to draw this little rectangle right here, and then you would be heavily underestimating. You still have a lot of area right here that you have not taken into account. And here's a quick overview. Over here, we can see the general equation for the trapezoidal method right here. Fxi is going to be your first data output point, and Fxi plus 1 will be your next. This quantity is then multiplied by the width of the interval, which is xi plus 1 minus xi. Now, if the subintervals are the same width, we then use the simplified equation below, where h is the width of the subinterval. And we can also think of h in this case as the step between each input. So this is a step, this is a step, this is a step, and they all have the same width. Now let's do a quick example using the trapezoidal method. So over here we can see that as you progress on the x, you go up by a value of 0.5. Now that is going to be your step, otherwise known as your h in this case. So we set h equals to 0.5. Now your fa is always going to be your first point, and your fb is going to be your last. And we're doing this over the entire table. So in this case, this would be fa right here. It means like this point is a, so this would be fa. And this point is b, so this would be fb. So we got those two. And now what about this? So basically what this is it's a sum of all the inner points in between. So these points right here. And how can you know? Well, we just move this h over here first. We can see that this is going to be your I1, this is going to be your I2, I3, I4, etc. And that's going to be your I12. And you can see that the sum starts at I equals 2 and goes all the way to n. Now, in this case, we have 12 points, which means 11 subintervals. So this is where our n is, and this is our n plus 1. Now that we have all this information, we can go ahead and start plugging in. So we can say that the sum from I equals 2 all the way to n is going to be 2 plus 8. Simply just put in all the points in between for the trapezoidal rule. So it's going to be 2 plus 8. And then let's just put that in the calculator very quickly. That gives us a value of 422. Now we can plug this into the full equation to get the integration. We get 235.5 for this case. All right. Now we move over to Simpson's 1/3 rule, which is a second-order polynomial approximation. Now this means that the unknown curve is approximated parabolically, as we can see on the graph to the right here. This method uses 3 points and 2 subintervals. Right, so here's our subintervals right here. So that's 2 subintervals and 3 points. Compared to the trapezoidal method. So over here we go up a point and up a subinterval. Now what does this change for us? This means that our estimates become a lot more accurate compared to the using rectangles and compared to the trapezoidal method that we just used. Here's a quick overview on the equations we will use. And in this case, F1 is going to be your first data output point, and Fn plus 1 all the way at the very end here is going to be your last. Now you might notice that sandwiched here in between these 2 points are the other points organized into 2 different sums. Now the first one, this first sum right here, contains even points, and this second sum right here is going to contain the odd points, both of them in between parentheses and multiplied by a coefficient. So in this case, the sum of your even points are going to be multiplied by 4, and the sum of your odd points are going to be multiplied by 2. And we will see what that means in just a moment. So let's work on an example. So over here, we can start by writing down our i's again. So our final point is going to be this one right here. We can set that as fn plus 1, which means that this is n plus 1, and this would be n, and then this right here would be our initial point. All right, so let's get started. So with this sum evens, we're just going to do the even points, so that'll be 2, 14, 36, 58, and 78, and then we stop here because this is our final point. And we simply just sum them up. Now plugging this in the calculator, we should be getting 188. Let me do the same thing for the odds. In this case, it's going to be 8, 28, 45, and 64. Now we stop there. Plugging that in the calculator, we should be getting 145. Now we're going to go ahead and plug those into the equation for I. And plugging that into the calculator, we should expect to see 188. Now, that was just covering these intervals right here. And that is where we will be applying our Simpson's 1/3. Because the Simpson's 1/3 likes to take even intervals, we take this as a subinterval, and then this, and then this, and then this, and then this. But then we are left with this extra point right here. So what do we do with that? Well, what we're going to do is we're going to take this subinterval as the trapezoidal method. So in that case, let's label this I1. I2 is going to be just the equation for the trapezoidal method. So our starting point in this case for just the trapezoidal method, we can ignore this as if this right here doesn't exist. Our first point is going to be 86, and our last is going to be 98. And then for I2, plug that in the calculator, and you should expect to get 46. Now, if we total these up, we're going to find that I is going to be 188 plus 46, so we can calculate I to be 234. All right. Finally, we're going to discuss Simpson's 3/8 rule. Now, it is a third-order polynomial approximation. So unlike Simpson's 1/3 rule, this method uses 4 points and 3 subintervals. So again, we go up a point and a subinterval compared to the 1/3 rule. Now, of course, this means that our estimates are going to be a lot more accurate compared to previous methods, and this method is the most accurate out of all the 3 we've covered in this review. Now here are the equations associated with this method. Over here, we're going to see the general equation again. And similar to the 1/3 method, F1 is going to be your first data output point, and Fn plus 1 is going to be your last. You might notice some small differences in the sum here. The first sum now has points starting at the second point and then jumping by 3. So you notice 2, 5, 8, etc. And with the other sum, it's going to be starting at point 4, also going up by 3. And both of them are multiplied by a coefficient. And we will see how this applies when the example comes up. Now here's the difference between Simpson's 1/3 and 3/8 method. Simpson's 1/3 rule is a quadratic curve, again, with 2 subintervals and 3 points. Versus Simpson's 3/8 rule, which creates a cubic curve. And we have 4 points and then 3 subintervals. Alright, now moving on to an example for Simpson's 3/8. We're just going to start by labeling our i's again. Now for this one, we are going to apply the Simpson's 3/8 rule over this interval right here, and then Simpson's 1/3 for this last one right here. Right, so this is going to be our final point, so that's going to be our fn plus 1, and this is going to be our first. Excuse me. So let's write that down. So f1 is going to be 0, and fn plus 1 is going to equal 78. Now, for the first sum, we're going to start at I equals 2, which is going to be this one right here. And then in the summation, we're going to take the fx at that point and then add it to the next fx, because it's the I plus 1 right here. So what that means for us is basically we're going to be taking them in chunks like this. So here's the first one, right? And then move on to I equals 5. I equals 5 is right here, all right? So we take this chunk like that. And then we move on to I equals 8. Right here, we take that chunk, and there we go, we stop. So let's write that down. So it's going to be 2 plus 8 right there as its own little chunk right there, plus 28 plus 36 plus 58 plus 64. Plugging that into the calculator, we should be getting 196. Now we're going to do the same, but for the last sum, and the last sum is a little bit easier. We're going to start at I4, and it's just going to be this point. And then we move on to the next one. We don't do anything else in here. And we just take 45. So for the next sum, it's going to be 14 plus 45. That's going to be for 4, 7, etc. Plug that in the calculator, or just do mental math, and then we get 59. Now let's plug that into the Simpson's 3/8 equation. Now label that as I1 because we're going to do a Simpson's 1/3 here as well. Plug that in the calculator, and we should expect to see 147. Now we're going to move on to Simpson's 1/3 rule. Now with Simpson's 1/3, we can ignore this entire part. Just treat that as if it doesn't exist. In this case, this will be your f1 at x equals 4.5, and this will be your fn at x equals, or your fn plus 1 at x equals 5.5. So in that case, we take the even numbers, and this becomes your I2. So for Simpson's 1/3, this becomes the I2. So we take this number as even. We don't have any odd numbers in between. That's why I plugged the 0 here for the odd sum. Now, solving that, plug it in the calculator, and we should be getting 86.67. Now we add I1 and I2 to get a final value for the total integration, and we should be expecting to get 233.67. Now, if we compare that to what we got before, this is a typo, that should be. Now, if we compare that to what we got before, we can see that the Simpson's 3/8 rule has given us the most accurate value. But we can see that overall, all of these numbers are very close to each other. So which method you'd like to use just depends on the application and how accurate you need your data to be. Here's a quick summary on what we've covered. So the trapezoidal method is a first-order polynomial approximation, approximates the analytical curve linearly, and it uses 2 points and one subinterval. Simpson's one-third rule is going to be a second-order polynomial approximation, approximates the analytical curve parabolically, and it uses 3 points and 2 subintervals. The Simpson's 3/8 rule is going to be a third-order polynomial approximation. It approximates the analytical curve cubically and uses 4 points and 3 subintervals. So in between each one of these, we have jumped up by 1 point and 1 subinterval, and therefore we have jumped up by 1 order of approximation. Here's a little cheat sheet that you can keep for yourself when it comes to the different equations for the different methods that we've covered in this short review. And I will also post the PDF or the slides for this after. Thanks for watching, and good luck on your exam.